Okay, we're going to continue with our applications of derivatives, now looking at optimization. So now we're going to take this idea of finding maximum and minimum values, and we can apply it to a broader range of applications. So for example, we have 40 feet of fence that's going to enclose a rectangular garden along the side of a barn. So one of the four sides is going to already be in place. That'll be the side of the barn. We want to know the maximum area that we can enclose using this 40 feet of fence. So if we let the width equal x, then the length is 40 minus 2x. We have 40 feet altogether, and our two ends are both length x, so subtract 2x for the remaining length. We know that area equals length times width, so area is x times 40 minus 2x. And we can multiply the x through, and now if we want to find the maximum or the minimum of some function, we take the derivative. And we set the derivative equal to 0. In this case, x equals 10. So this is going to be a local maximum because at the extreme, either x could be 0 or x could be 20, in which case we'd have an area of 0. Now, if you're unsure about that line of reasoning, you could just make a number line and confirm that that is in fact where the maximum is going to be. So the width is 10 feet, the length is 20 feet. And the question asks us for the maximum area that we can enclose, so we'd better figure out what that area actually is. So we multiply the length times the width. 10 times 20 gives us a total area enclosed of 200 square feet. So in general, if we want to find the maximum or the minimum value of a function, and we've seen this before, we write the equation, but the key here, because we're going from a word problem, is we have to come up with our equation, and we have to make sure that our equation is in terms of just one variable. On that previous example, we had that area is length times width, so we had to describe the length in terms of the width in order to go through and solve. Then we find the first derivative, set it equal to 0, and you'll have to either check the endpoints or use a number line to determine if this is a maximum or a minimum. Okay, so we have a can, and this can is going to be cylindrical in shape and have a volume of 1 liter or 1,000 cubic centimeters. We want to know what dimensions are going to use the least amount of material. So we're going to minimize the material by minimizing the surface area. So area is 2 pi r squared. So area of a circle is pi r squared. There's a circle on top and a circle on bottom. And the surface area of the outer portion is going to be a rectangle if it was unrolled, and that rectangle is going to have a length of 2 pi r, because that's the circumference of the circle. So 2 pi r times the height is going to give us the surface area around the outside, so we add those all together to come up with the entire material. Okay, so one issue we have now is we have two variables, r and h. So we need to find some way to get this down to a single variable. Whenever this happens, there's going to be some way you can use a substitution. And the additional information that we haven't used yet is that the dimensions of, or that the volume of this can needs to be 1,000 cubic centimeters. So we know that volume is pi r squared h. The volume is 1,000. We're going to solve this for h. So h equals 1,000 over pi r squared. So substitute that in and simplify the equation down. So we have an expression for the area just in terms of r. Now we can take the derivative. We can set the derivative equal to 0, and we can solve for r. So r, if we plug this into our calculator, is approximately 5.4193 centimeters. To find the height now, we have an equation that gives us h. So plug r into that equation, and we find the length or the height of the cylinder. Okay, if our function that we're trying to optimize has more than one variable, we need to use substitution to rewrite the function in terms of just one variable. And if you're not sure that the extreme you found is going to give you a maximum or a minimum, you have to check. That's where you can use endpoints or use a number line. But often in the context of the problem, once you've found your critical point, you can conclude if that's going to be a maximum or a minimum. But if in doubt, double check.